Hello young men, welcome to the Wake Young Men's Leadership Academy Smart Video Lab. I'm here to talk to you guys about linear functions and help you review for the test on Monday if you're in A-Day first period, or on Tuesday if you're in B-Day third period. So we're going to review linear functions and the many forms of linear functions that we've looked at. So let's begin first by talking about what a linear function is. So one key topic that we need to refresh ourselves on is rate of change. So remember, rate of change is always just the change in the dependent variable divided by the change in the independent variable, or more simply, change in y divided by change in x. So for a linear function, the key defining characteristic of a linear function is that rate of change is constant. We call that slope. So you could have rates of change for nonlinear functions, but it wouldn't be called slope. So slope is only for a linear function. So let's say I wanted to look at a table of values, and I wanted to make my table of values represent a linear function. We'll start with an easy example. X is going up 0, 1, 2, 3, 4, 5. Let's say y starts at 10, and it goes up 12, 14, 16, 18, 20. Question is this a linear function? Yes, it actually is, because the rate of change is constant. Change in y divided by change in x in this table is always going to be 2. So the rate of change is a constant 2. So let's look at one example. If I look at this column and this column, my change in y is 18 minus 14. My change in x is 4 minus 2. So that's 4 divided by 2. Which is 2. Yep, so the rate of change is 2, looking at those two values. And you could do the same thing, picking any two columns. You'll see that the rate of change is 2, which makes this a linear. So let's say I want to make another table, and I want it to be a linear function with a rate of change of 2, but let's say the x values are going up by the same amount every time. And actually, I don't like those values. I'm going to change it a little bit. 0, 1, 2, let's say we jump up to 10, and then 20, and then 50. And let's say again that y is starting at 10, so it'll start off the same, 10, 12, 14, but oh, now the x doesn't go up by 1, the x goes up by 8. So change in x there is 8. So I need a change in y of 16, so that the change in y over change in x will be 2. So this is going to have to go up to 30. So let's look at this. Make sure we did it correctly. Change in y here is 30 minus 14. It's not a very good 14. Here we go and erase that. Here's 30 minus 14. Change in x is 10 minus 2, so that's 16 over 8. Yep, there's the 2 that we wanted. So if I go up by 10 now in the x, I'm going to have to go up by 20 on the y, so that'll be 50. If I go up 30 on the x, I have to go up 60 on the y, so that'll be 110. So this is a linear function, again, with a rate of change of 2. So now let's say we want to look at a linear function on a graph. So I'm going to just draw a random graph here. And there, I like that. Let's want to get a good one. Yeah, that looks like a good one. Okay. So if we've got a linear function on a graph, change in y over change in x from a graph, the slope can be found using something called rise over run. Because this axis is the y-axis, this is the x-axis. So as the y-axis changes, that's rise. And as the x-axis changes, that's run. So change in y over change in x is rise over run. So the slope of this line I could find by picking two nice points, let's say here and here, and then looking at my amount of rise divided by my amount of run. So this would be a rise of 1, 2, 3, 4, 5, and a run of 1, 2, 3, 4, 5, 6, 7. So the slope here would be 5/7, rise over run. And remember, it's a positive slope because as we read the line from left to right, it's increasing. Let's suppose now we want to look at another graph. This time the slope is negative because as you read the line from left to right, it's decreasing. But again, slope is changing y over changing x, which from a graph is just the rise over the run. So let's pick some good points. I've got a point here that I'm going to use, and I'll use this one here just to be easy. So the rise there is 3, the run is 1, but we said the slope is negative, so it's going to be -3/1, which is -3 is the slope for this graph. So there's one other interesting feature of this graph that we haven't talked about yet, and that's the y-intercept. So here's the y-axis right here that we're looking at. So the y-intercept is going to be where the line intercepts or hits that y-axis. So in this case, it's right there at that point, which is 0, -1. So that leads us into something called slope-intercept form. The easiest way to write the explicit function rule of a line when you're given a graph is in slope-intercept form. So to do that, all I need is a slope and a y-intercept. So slope-intercept form is y equals mx plus b. Remember, m is the slope, and b represents the y-intercept. So in this case, we have a slope from our graph of -3 and a y-intercept that's at 0, -1. So we'll just write that rule as y equals -3x minus 1. Slope times x, and then minus the y-intercept in this case because the y-intercept is negative. Let's look at another example. What is the explicit function rule for a linear function with a slope of -3/4 and a y-intercept at 0, 3? Well, that's easy. Y equals slope times x, -3/4 x, and then plus 3 because the y-intercept is at 0, 3. So notice that the x value at a y-intercept is always 0 because when the graph hits the y-axis, x is always 0. So let's say we want to graph this linear function rule now that we just made. So whenever you're graphing linear functions, you always want to start with the rule first written in slope-intercept form, which we have. That's in slope-intercept form. So we want to start at the y-intercept, which is at 1, 2, 3. Now we're going to use the slope. It's a negative slope, so I know my line is going to have to be decreasing in some way, like that. And the rise over the run, change in y over change in x, for this case, is my slope, -3/4. So we're going to go down 1, 2, 3, and write 1, 2, 3, 4, and plot that point. That was down 1, 2, 3, and write 1, 2, 3, 4. And then I could do the same thing in the other direction. I could go up 1, 2, 3, and left 1, 2, 3, 4, and plot that point. And my function comes when I connect those lines. And that's a bit sloppy, but I could do a better job if I had a ruler. Let's look at another example. The graph below shows the height of 2 seagulls above the ocean over time. And let's say that we want to write the linear function rule in slope-intercept form for both of these seagulls. So let's start with the blue seagull. Probably actually wasn't blue because I've never seen a blue seagull, but his graph, the line is blue, so we'll call him the blue seagull. So we're going to need to find his y-intercept. Well, that's easy. That's where the graph hits the y-axis. There at 20. And now we need to find the slope of this seagull's line. So let's find some nice points on the graph. And the easiest one is usually the y-intercept where it started. So we'll use this point, And let me find another nice one. This one is surely a nice one. So now we have to pay attention to our scale. We rise from 20 to 80, which is a rise of 60. And we run from 0 up to, that's at 90. Run 90. So the slope, change in y over change in x from a graph, rise over run, is my rise of 60 divided by my run of 90, which simplifies to 6 over 9, which simplifies to 2/3. So now I have a y-intercept and a slope. I can write the rule for that blue seagull. Y equals 2/3 x plus 20. So I'll write that up here next to the graph. Y equals 2/3 x plus 20. Now what does that mean, that slope mean in the context of this problem? Well, the change in y, the y-axis, that's 2 feet for every 3 seconds. So the height of this seagull above the ocean increases 2 feet every 3 seconds. Now let's talk about the red seagull. Again, he probably wasn't actually red. And I may have spelled seagull wrong, but I'm not sure. This time, we want to always start with the y-intercept, which is here. So the y-intercept is 90, or you could write that as the point 0, 90. Remember, x is always 0 at the y-intercept. This time the slope is negative, but we still have to use nice points and find the rise over the run. So I'm going to clear off this other stuff from the other graph so we can see. So let's use this point, and this looks like a nice point. So we rise, or we go down from 80 to 30 there. So that's a rise of 50. We're going down, so really it's negative 50. And then the run is 10, 20, 30, 40, 50, 60, 70, 80. Or from 0 to 80, that's 80. So my slope this time is negative 50 over 80, which is negative 5/8. And this time I'm just going to show you guys a bit of a different example, convert that to a decimal. So as a decimal, that would be negative 0.625. So I could write this rule as y equals negative 0.625x plus 90. Now what does this slope mean? That's negative 0.625 feet per second. So the height of this seagull is decreasing 0.625 feet every second. So that guy is going so slow. And that's it for our linear function review in terms of slope-intercept form. If you'll go to the next video that's posted called point-slope form, that will show you that form and give you some more practice with that. Oh, and if you watch this video, extra credit code on the top of your test, write NC State. You'll get 3 points on your test.